Alright, so you're being recorded, don't say anything stupid. Alright, here we go. So this is a really good video action. Short, it's only a minute 57, it's good though. Here we go.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has one valence electron. With a stable...
Watch the beginning again.
Ionic bonding occurs between two...
The white one is sodium, and the green one is chlorine. So you have Na and Cl coming together to make NaCl. That's an ionic bond. Metal, non-metal. But watch what happens. Those little yellow things are electrons kind of moving around right outside the nucleus. So notice what happens to the size of these two and who loses the electron, who gains it. Because this one example applies to every ionic compound. Every ionic bond, every ionic compound does the same thing. It's just the two elements will change. This could be any metal. Is that a sneeze? Bless you. This could be any metal. That could be any non-metal. So this is very simple the way they show it. I think it's good. So watch again. Pay attention to the size of these two and then what happens to this electron right here.
Two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom.
Okay, so what happened? What happened to the white one? Get bigger or smaller? Smaller. What happened to the green one? Bigger. Why? It took its electron. I think of the electron as like food, right? So the green one ate an electron, so it got bigger. Okay, you eat enough food, you get bigger, right? This one, I guess got rid of it. I don't really have a great analogy for that. I mean, I guess you could throw up enough, you lose weight. But that's kind of gross. So the metal loses something, shrinks. Non-metal gains something, it gets bigger. That's because now you have Na plus and Cl minus. So Na lost one electron. Why? Because Na is 281 on the periodic table. It wants 8 valence. So what it does is it loses that 1. So Na plus becomes 28. Cl is 287. It wants 8. So it gains this 1 electron and becomes 288. So it's a win-win situation here. Na loses, Cl gains, but in the process they come together and make a bond, a strong ionic bond, using their ions, why it's called ionic, and as a result they both have a complete octet, and everybody's happy. Full valence shell, so it's stable. So that's the gist of ionic bonds. I'm going to play the rest of the video. But metals always give their electrons to nonmetals, and that's because nonmetals have higher electronegativity. When he said in the very beginning here, right here, there's sufficient energy to take an electron.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom.
Right, so this Cl has a high electronegativity. It's like 3.2. Na is like 0.8 or 1 or something. So when they're fighting that tug of war for electrons, the metal completely loses and lets go. In other words, the analogy of holding on to the rope, imagine Cl literally rips the rope right out of Na's hand. So Na doesn't have it anymore. Okay, Cl has everything. That's because the electronegativity is very high versus very low. So that's ionic, but I'm going to let it go.
A sodium atom has one valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electron.
So watch what happens to that 1 electron. It'll actually end up going back and forth, almost like a figure 8 thing, but that has nothing to do with anything. It's showing that the electron's being shared. It's the best video I've ever seen for this because it's really hard to visualize and understand this stuff because it's so small and tiny and hard to really show you in real life. So this is a good video because the last example of ionic, that little electron went to Cl and just stayed over here. You're going to see this electron go back and forth, meaning sometimes it's over here, sometimes it's over here. That's what they mean by share. So ionic, there's a transfer of electrons. Covalent, they share electrons, and covalent doesn't involve metal at all. It's two nonmetals. This actually is hydrogen, and that's oxygen. So they share electrons.
The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with one valence electron needs one additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still one short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
Okay, so that's exactly what I have on the board here. So water, you have 2 H's, 1 O, you know that. But this now oxygen, if you count, has 2, 4, 6, 8 dots around it, and hydrogen has 2. So when hydrogen gains 1 electron, when it bonds, it kind of gains. It shares that X there, or that dot, either one. Instead of 2, it has 1 like helium, so it's stable. And then oxygen gets to share them as well, so instead of 6, it'll have 8. So that's why covalent bonds bond, that's why they're formed, because everybody gets a stable outer shell. Helium or hydrogen can never have 8, but it can have 2, just like helium, and that's good enough, because that's full for helium. So what's the gist of all of this? What is ionic? Metal, nonmetal. What do? Transfer electrons so they can become stable. Covalent, what is it? 2 nonmetals, two or more nonmetals, right? We have 3 technically here, 3 atoms. So nonmetals, and then the nonmetals share electrons. Why? So they can be stable, full valence shell. And that's it. If you can remember those 2 things, that's good enough. Well, I guess technically it's 4. Ionic is metal, nonmetal, that's the one thing. And then they transfer electrons. So that's the second. The third thing, covalent, is 2 nonmetals, and then they share electrons. So if you can remember those things, you're in good place. Questions on that? Again, I know this is kind of like class, so I apologize, but we gotta make sure we know what we're doing. Okay. So I will play the music video because it's funny and entertaining, and it's pretty good. He does a good job. But first, let me ask you, do you know the difference between polar covalent and non-polar covalent? If you don't, that's okay, but we're going to go through it right now. First of all, I like to think of ionic and covalent as different continents. So like ionic is over here in Asia, covalent's over here in North America. Okay? Completely different. Why is that important? Because over here in North America, you have covalent. And then there's 2 parts to that. There's polar and non-polar. So maybe I should put it on the board so you have a better idea visually. Ionic's over here, and then separated by massive amount of space here. Covalent is over here. And then off of covalent, you have polar and non-polar. I'm making this clear right now because there are kids who always try to tell me that something is ionic and polar. I used the analogy yesterday. That's like telling me the color blue is big. That doesn't make any sense, right? Colors can't be big or small. I mean, my mind just exploded trying to think of that, okay? So, to you, saying ionic and polar are the same thing, maybe you're confused, you don't know how big of a thing that is. That's really insane because that makes no sense. Ionic is completely separate on its own thing, okay? So polar and non-polar are part of the covalent, like umbrella. So you have covalent, and then those 2 are underneath it. Ionic is a whole separate deal. So that's the first thing I really want to make clear, that these are only part of covalent. So now, let's talk about the difference. So I'll give you one example of each. So for polar, and again, if you're having trouble with this, you should write this down. And for non-polar, it's all about the symmetry. It's really what it's about. And it's about electronegativity. I know Mr. Herodes taught you guys the difference between, if you subtract electronegativities, you can figure out if something's ionic, polar, non-polar. And that's 100% correct. That's a good way to do it. I think it's kind of confusing for some students. If you can remember the numbers, then you're good to go. But if you can't, this is kind of another way to look at it. So I'm not going to really go through the numbers again because I know he went through that with you. So a different way to do it is symmetry. So if we look at something like methane, CH4, that's nonpolar. If you look at water, which is the most common polar molecule asked on regents, I would say, let's draw the dot structure. So you have to be able to draw dot structures or else you can't do this. So water, like I just did before, looks like this. And if you draw an X and Y axis, so I know I'm way over here, you guys can see, right? We're good, the pole kind of in the way. Just move, you have to, move your head. So if you draw an X and Y, or a Y and X axis, this is not symmetrical. In other words, there's no mirror image of the H's on the other side. Because this is asymmetrical, we say it's polar. All asymmetrical covalents are polar. If you look over here, CH4, oops, I'll put the dots in. If you look at CH4 and you draw your X and Y, that is very symmetrical. There's mirror images all around. So they mirror image of the H's up and down, left and right, X and Y axis. That's symmetrical, so that's nonpolar. The other stuff that we talk about with these is because this is asymmetrical, it's unequal sharing of electrons. They share unequally. Nonpolar share completely equal. And it has to do with electronegativity. CH4 has a very small difference in electronegativity. C, I think, is, I want to say 2.6, and H is 2.2, so that's a 0.4 difference. And if you look here, H is 2.2, O I want to say it's like 3.5, but that might be a little high. But if you subtract those, that's 1.3. So there's a big difference in electronegativity. That's because oxygen wins that tug of war. So all the electrons are going that way. That's called a dipole moment, going towards oxygen. Here, we don't have those. Nobody's winning because it's symmetrical. Plus, their difference in electronegativity is very small, meaning not really one, how am I going to word that? One of the atoms doesn't pull any stronger than the other, not really. So nobody really wins. So they share equally, they share unequal. So I'm just going to write that, unequal, and this is equal. Okay, there's a lot I'm not writing, but again, this is a kind of review. I've gone through this in class a couple times. I know Mr. Grotis did, so I'm not writing every little detail. So what do you need to know? First of all, these two are covalent. Why? Non-metal, 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 non-metal. Next thing you need to know. This is asymmetrical, this is symmetrical. How do you know? Do the dot structure. If you draw the dot structure, you can do your X and Y, you can see who's symmetrical and who's not. Okay, as a result, if you're in period 5, this is those little 8s, but they're not 8s, you have a partial negative on the O and a partial positive on the hydrogens. And that's because the electrons are getting sucked that way. Oxygen's pulling them that way. Partial negative, partial positives are called poles. Polar has poles. Here, there's no poles. No partial charges. Everybody shares equally, there's no partial charge. The last thing, I know I'm going quick, but the last thing I'm going to tell you, sometimes kids really learn well and sometimes they don't. We'll find out, I guess, down the road. So listen carefully. Once you have determined, okay, I know this is ionic, I know this is covalent. So once you've determined this is covalent, this is covalent. So water's covalent, CH4, which is methane, is covalent. And I ask you, okay, which one's polar, which one's non-polar? Instead of drawing it and kind of doing all this work, there is a shortcut. And I'm hesitant to teach it, but I'll tell you because it might help on at least a multiple choice. Short answer, it won't work because you have to explain this. But multiple choice, here's what you do. You look at the last subscript of the compound. So H2O ends in a 1. You don't see it, but there's a 1 there, right? There's 1 O. CH4 ends in a 4. The way this works, and it works every single time, is if it's an even subscript, it's nonpolar. If it's an odd subscript, it's polar. And that should make sense if you understand symmetry. Not to be weird, but if I was to chop off one of my arms, I wouldn't be symmetrical anymore because I only have 1. If I have 2, I'm balanced. So even numbers are balanced, they're symmetrical, right? Look at here. If I change that 4 to a 3 and get rid of that H, look up here. If I get rid of that H, it's not symmetrical. We'd be over here, polar. So it should make sense to you. If it's even, it's going to be symmetrical, which means equal, which means not polar. And if it's odd, you're not going to be symmetrical. Unequal, that means polar. So a lot of kids kind of take that little trick and they really hang on to that, and that helps them, and that's fine. But if I ever ask you why is it polar, why is it non-polar, you can't tell me because the subscript's odd or even. That's not an acceptable answer. So that's my quick crash course with the polar, non-polar. Hopefully it makes some sense. Just a couple more examples. All the honcoglyphs, H2, O2, N2, Cl2, all those are non-polar, right? They end in 2's. Carbon dioxide, CO2, non-polar. Over here, NH3, ammonia, PCl5, those are odd, they're polar. So again, that's the difference between those two. So hopefully I said something here today that makes some sense. All right, let me show you the video here from this guy, because definitely it's worth watching. He goes through ionic and covalent, kind of repeats himself a little bit, but sometimes kids remember these little videos. They remember things. A little jingle gets stuck in their head. So it's worth it. I'll show you this, and then if there's time, I can start metallic bonding. If not, we do have to do this next lab. I do have to teach you metallic and networks solids, and I don't have time in class. So that's just where we're at right now. All right, so here we go. Try to contain yourself, though.
Ionic bonds, covalent bonds, both of them chemical bonds. How are they made? What's the difference? Watch, you'll see. First we'll start with ionic bonds. A metal and non-metal are involved. The metal gives over electrons, the non-metal it receives, they actually call ions. The metal might have 1, 2, or 3 electrons for the non-metal to receive. It all depends on what's needed to make the number 8 for the non-metals our share. And if it happens for them, they both become ions, charged atoms, they become ions. The metal's positive, the non-metal's negative, they become ions, oh yeah. The metal's plus, the non-metal's minus, and opposites they do attract. So what you get when they come together is an ionic bond. Sodium, chloride. So what about those covalent bonds? It's not about loss or gain of electrons. Valence electrons, they are shared to complete the outer shells of the non-metal side. It's when non-metals join to make